Hello everyone, welcome to the second lecture of our week on SAR image analysis in our course AI for Earth Observation. In this week, in the previous, that is the first lecture, we have discussed various basics and why would we like to use SAR in comparison to optical multispectral images. Thereby, we have also discussed how deep learning can play a role in SAR image analysis and what are the different tasks that we can perform with SAR images and deep learning pipeline. So there we have image classification, semantic segmentation, change detection, as well as object detection. So we will discuss some architectures or some training mechanisms and nuances related to the SAR images architecture in our subsequent lectures. However, in this lecture and also the following lecture, we will talk a bit about object detection basic architectures. Object detection is very important in the context of SAR image analysis. There we have already mentioned that ship detection, building detection, such target detection talks are very popular in the scientific literature. However, object detection is something also, of course, very useful, very important in computer vision in general, and also like even if we talk about Earth observation with respect to optical images as well, even then this is crucial. However, we have not studied about the object detection architectures in our previous weeks, so here we will get some exposure to that. More specifically, we will talk about RCNN family. Just like image classification, semantic segmentation, in the object detection also there have been many architectures, many variations. However, RCNN family is indeed one of the most popular and also, in my opinion, one of the most intuitive approach to object detection. This is the reason we will discuss RCNN family. So with this, let us go ahead. So object detection, our goal is to identify object location. We will assign a bounding box to each object, and also we want to identify the object category. How is it different from image classification? In the image classification, rather, we were assigning a single category for the entire image. How is it different from semantic segmentation? Semantic segmentation is a dense task. However, there, like we are trying to assign label to each pixel. Whereas in this particular case, okay, we are just confining ourselves to objects of interest, and corresponding to those, we are trying to find bounding boxes and those bounding boxes category. Output consists of class labels and the bounding boxes. it's indeed more challenging than mere image classification, where we are just trying to assign a single label to the entire image. Whether we can say that this is more challenging than semantic segmentation or not, I mean, this is a bit not so objective question, or like there is no really objective answer to it, I will say. Both semantic segmentation and object detection, they are challenging in their own way, I would say, depending on like exactly what your task is. You would probably like to choose either of these two. Like, let's say you are thinking about a marine scene, like a scene which consists of entirely the sea, or like some port coastal areas as well, and your interest is only to find the ships, right? What do you even do with assigning labels to each pixel there? Most of the pixels are probably water, or some large, depending on the spatial resolution of the sensor. Some marine animals can be captured. There can be other artifacts as well, of course. So there, we are not interested really in anything except the ships, right? So obviously, we would prefer in such a context to go for object detection rather than semantic segmentation, assigning labels to the each pixel. Of course, the other way is like going for a binary semantic segmentation, where you just try to identify the pixels as shape or not shape. So that possibility is also there. I will see like how the object detection is generally approached. This is significantly also different from how semantic segmentation is generally approached. Indeed, object detection is very important in art observation. Many art observation SAR image analysis tasks are modeled as object detection. Again, depending on the resolution and all. So it could be ship detection, it could be building detection, it could even be vehicle detection. Let's say like we are talking about high resolution SAR images and vehicle detection. This is something important from the security defense perspective as well. The challenges in object detection include the fact that the objects often appear at different scales. The occlusions and clutter may complicate the recognition. Multiple objects may even overlap in an image. So these challenges are a bit more generic, I will say, like it's not just with respect to the SAR images, the challenges listed here. Now, let us try to think of a possible basic pipeline for object detection. Let's say we have a sliding window which searches through my given image, the entire image, okay? So the window is of course much smaller than the image itself, but window goes through the image and goes across the image and it searches the entire image. Handcrafted features are, let's say, extracted, or somehow features are extracted, and let's say independent classifiers are applied on for each of these windows. So this is the window that you are sliding through the image every time you are extracting features, and every time you are, let's say, like for simplicity, let's say that we are just interested in one object. Let's say this object is some kind of vehicle, okay? So this vehicle classifier, this is now applied every time on this window, and whenever your classification output is positive, then you say that okay, this particular window, this consists of, this has a like a target object. Such an approach, and here of course I kind of modified the object detection problem to specific target detection problem. In practice, often we will be working even with multiple objects of interest. And this overall approach, as you can see, like this indeed will incur high computational cost. Even though the very first version of RCNN that we'll study is kind of similar to this possible basic pipeline. Yeah, so this possible basic pipeline has several limitations, including that the exhaustive search itself is inefficient. There, of course, I mean, as I said, that the RCNN has similarity to this pipeline, but not exactly the same. There, we don't really go for an exhaustive search, as we'll see soon. Most image regions indeed contain background, so we need to, like, we need some kind of mechanisms to focus on, like, like a more selected number of windows instead of like, like taking a sliding window and let's say like slide in 1 pixel or 2 pixel every time. So what we need basically is some kind of region proposal, and this was included in the RCNN, which can reduce my search space. And as in the last slide, we talked about handcrafted features. Instead of handcrafted features, if we can use CNNs, we can possibly enable powerful feature extraction. So with this, we are now almost ready. Some background may be still needed, but we are almost ready to talk about RCNN, which is one of the first CNN-based object detectors. It combines region proposals with deep CNN features. So if we think about this basic setup that we talked about a couple of slides back, compared to that, the major improvements are these two steps in the RCNN. In the subsequent versions, we'll see even more modifications, but in the basic RCNN, these two are the major modifications. And it provided a significant improvement over the methods that existed back then. So before actually discussing about RCNN, let us just take a more non-technical example. Just think of an admission process to a particular department's master's program. Many of you might be either even like studying your master's or have completed your master's, or maybe even if you're in bachelor's, let's say like some of you might be preparing for a master's, right? So I'm assuming that, okay, like why I'm saying that, okay, like this all might be your background, that to assume that most of you actually are familiar with how the master's program admission goes in most of the departments. Again, this is again something not uniform, of course, but in most of the places how it goes through is, let's say the department receives a few thousand applications. Let's say it receives 2,000 applications or so in a particular admission cycle. In that case, you would probably not take everyone to the next cycle, right? You would apply some kind of shortlisting, okay, criteria that could be based on GATE score, that could be based on CGPA or something like that. Okay, of course, could be a combination of those aspects to actually identify a much like shorter number of candidates. Now, let's say like you now call like just a couple of hundreds of candidates starting from the 2000 actual candidates, not maybe not even couple of hundreds, let's say 100 candidates or so. Now, not necessarily. Let's say these candidates, I'm saying that okay, you have called them to like a next level of like selection process, which could be a written test or an interview. My example probably goes better with an interview, and I also realized now that my example goes better with rather than just a master's program, maybe with like there are masters by research program, it goes better with those. So for admission to such masters by research program, often what happens is that you are assigned also to a particular research area at the admission itself. In a just a visual masters, you will not be assigned to that, but in a master's by research program, you will be probably assigned to let's say one particular research area is graph machine learning, one particular research area is speech analysis, one particular research area is computer vision. So these three are the let's say candidate research areas, and you will be assigned to one of out of these three. So this 100 candidates, I said, like starting from 2000, this 100 or 200 candidates were called for the next round, which let's say is an interview. Are all of them assigned to one of these three categories? No, right? Many of the candidates will actually be also rejected in this round. So in a way, like even though I talked about three particular research area where the candidates are assigned, in practice, this is not a three-way assignment. In practice, this is a four-way assignment, right? Where background is also a possibility. So this is how in most object detection methods also works. Like if you have this candidate, otherwise you will not assign each of them to like one object, like your objects of interest. Some of them will also then eventually be assigned to background, which basically is like saying that okay, like if my objects of interest were building, shape and vehicle, and the background is basically okay, neither of these three. Okay, so the RCNN is just like how I described this admission process to a master's by research program, where there is a first round of shortlisting and then there is a second round. Similar to that, the RCNN is also a two-step or multi-step process where the object proposal generation is decoupled from the classification itself. So the first step is you are generating the possible object proposals instead of like going through a like an exhaustive sliding window kind of mechanism, which would have become computationally much expensive. You would try to generate some object proposals, and then on the top of them you will try to do classification and also bounding box regression. That's another part of the story. Let me come there soon. So the proposal generation itself, just like in the previous example, eventually you wanted to assign the students to these three particular research groups that I talked about, right? Graph machine learning, speech processing, computer vision. But the initial proposal generation, which was based, let's say, on the CGPA or GATE score, that did not involve really, already checking out the background that, okay, whether the candidate is suitable for any of these particular research categories or not. So similarly, a or most of the such two-step, I'm not just talking about RCNN, most of the such two-step processes of object detection, they will not think about classes itself already in the like the proposal generation mechanism. This is better kept decoupled. Okay, so with this, let us now start thinking about the RCNN pipeline. The pipeline will go like this. We'll start by generating region proposals. We'll warp each proposal to fixed image size. Why would we do so? We'll come soon to that. We extract CNN features independently for each of these region proposals, and then we perform classification, that is like, okay, which of the objects of interest this particular RY region proposal belongs to, and also we will further, so this region proposal, this is basically like, it's coming as like a bounding box, right? So but this initial bounding box itself may not be that perfect, so we'll eventually do another round of bounding box regression. Okay, so now let's look at this a bit more pictorially. Given the image, as we can see that, okay, the region proposals have been generated. Region proposals will be generated using mechanisms like selective search, which, I mean, we're talking about RCNN. So in this case, okay, the region proposal generation itself is not something like, okay, is deep learning based. So region proposal generation, as we can see in this particular case, we have mentioned that about 2000 per image. Of course, this can be a bit of like a parameter. You could, like in your own version of RCNN, you could generate probably even less number of proposals or even more. But that's what the RCNN original authors found to be like a suitable number. And from there, so each of these region proposals, as I mentioned already, we bleed down to a fixed size. And then on the top of this, you would be applying CNN to obtain CNN features. And then we have to classify them. So interestingly enough, the original RCNN paper, and this was so long back, like about 11 or 12 years back from now, I think it's a 2014 work. If I remember well, in the footnote I have mentioned the paper title, but not the year, of course. So what was happening is that they were still using SVM-based classifiers in the original RCNN paper. So, I mean, how do you justify using SVM-based classifier? Of course, this was later not used anymore in the later versions, which we'll study in next lecture. However, how I personally justify, there are two things to note. One is this makes RCNN really modular. There are several modules like, okay, region proposal generation itself is a module, the feature extraction itself is a module, where CNN is coming, okay, and then the classification itself is a module, okay. So it makes it quite modular. And yeah, I mean, SVM-based classifiers, optionally bounding box regression. Let us not discuss so much about bounding box regression now. We'll be coming back to that in the context of fast RCNN. So now, this is one justification. The other way of justification is a bit historical, I will say. How I also think, I mean, of course, the original authors would be able to tell us better why they thought of this design. And I have not seen any, like, they may have given this reason somewhere in some interview or some other paper, but I don't remember reading or seen any such interview. But how I personally believe is that like the reason is historical, in the sense that think like this manner, that SVM, this indeed was the dominant choice in computer vision till 2011, till from 2012 with AlexNet, or late 2011 starting 2012 with AlexNet, things started changing. But of course there is some like a transition period where like people started adopting CNNs, but they were still so much habituated to using SVM. That's why it's kind of like at that point of time it's very difficult to think of a particular framework where they are still not using SVM in one way or the other way. The same thing we can observe right now, like with the adoption of the vision transformers and all. Still we see like in most of the frameworks of, I won't say most, but still quite often we see that with the vision transformers somehow CNN is also used. A combination is often used. Okay, talking about the region proposals itself. Region proposal generation methods take an image as input and provide us with the bounding boxes that are likely to be object. The region proposals itself can be overlapping, and the region proposals can be quite noisy as well. I mean, as I said, that the original RCN paper, we're not just talking about like 10 region proposals or 20 region proposals that generating 2000 region proposals, but still better than taking sliding window, and that sliding window itself will be of different sizes you need to consider, right? And then going through the entire image. So it's still much better than like 2000 is much better than that. Now still like, okay, 2000 is much better than that, but if you like try to visualize 2000 such proposals in an image, of course that's not going to be like nice to look at. Even if it was not 2000, even if it was just a few hundreds, even then like it would be quite not so easy to visually judge what's happening. So one of the dominant method for this region proposal generation is selective search, which considers color, texture, size, fill, these aspects, and based on this it generates region proposals. We will not invest so much time in this, but it's important to understand. I mean, this is something which doesn't really involve deep networks, but it can generate the region proposals for us. Yeah, one aspect which of course we need to understand, not just for selective search, rather for like any such mechanism that we would probably use in such a region proposal generation stage, we need something with high recall, right? And at the same time we need to keep the computational cost moderate. If we adopt a particular method which does the job well, but has a really high computational cost, it doesn't make sense, right? Because at this stage we are just trying to generate some rough proposals, which you see many of these will be just discarding. So similar to this shortlisting, shortlisting based on the GATE score or CGPA, we still call a few hundred students, right, for the next stage, which could be interview or written test, whichever. But in the next stage only, we probably reject a high number of candidates, right? So high number of candidates are just assigned to the background in our CNN language, whereas only a few will be assigned to those particular 3 classes that we are talking about, 3 research categories. So in the same way, the buildings, vehicles, and the ships here also will be these particular classes will be out of 2000, maybe only few, and rest will be background. And then we also have a bounding box regression also. So Yeah, that's the reason. I mean, at this stage, we don't need to be, like really, really very good, but we need to be careful about the computation cost. So, yeah, I mean, now coming back to the RCNN again, the region proposal generated, and the next stage, as you can see, is going to RYs, which will be fed through the CNNs. However, uh, for to obtain a feature vector from the CNN, we need to feed fixed size images, right, to the CNN. Let's say 224 cross 224, 112 cross 112, or some fixed size. So there is coming the something that I already mentioned, that will be resizing these region proposals, which are each of like different shapes, and they will be resized to form fixed size ROI, which is to be fed to the subsequently to the CNN to obtain the feature vectors. Yeah. So this is what I was just talking about, that the proposed regions are the different sizes, and the issue is that then we cannot just fit to CNN and obtain feature vector if they have different sizes. Thus, we need to resize them. So there, the region warping is coming into play. Each proposal is resized to fixed resolution, and it enables processing by a standard CNN. But of course, it also comes with the drawback that different RYs with different aspect ratio and all, I mean, they can be resized to the same fixed resolution. In a way, you are in that process also losing some information. Then comes the feature extraction part. Forward pass for every region proposal. The deep CNN extracts high level representation for each of these given RYs. Here also, there is a challenge that needs to be considered. That is, so to understand the challenge better, let us ask ourselves this question: will a generic pre-trained CNN be good enough? So why I am saying that a generic pre-trained CNN, I mean, when I'm asking this question, probably the answer is no. That's why I'm asking this question. It's not that difficult to guess. So why I'm saying that generic pre-trained CNN might not be good enough for our particular case. The reason is that, in a way, like, you can think of this as a kind of domain shift, right? Like, let's say your CNN was trained with, like fixed, let's say 224 cross 224 images. And now what you're feeding is rather, RYs, which are sampled from it, the region proposal sampled from it, and then they are also of different sizes. Then reshaped, of course, that's a different thing, but reshaping doesn't actually alter that fact that, okay, those region proposals, their focus is on like much smaller area of interest in the image. So this, in a way, is a domain shift. Domain adaptation itself, I mean, we will be discussing later. We have mentioned the domain adaptation, importance of domain adaptation several times already in the course. We cannot really, go for, a proper domain adaptation kind of mechanisms here. Rather, we need to, think about some simple approach, how we can, account for this domain shift in this particular case. And there comes a solution that the CNN let us fine tune on the cropped images. Okay, so CNN, let's say this was initially pre-trained on ImageNet or whatever, and now let's say, like, using the selective search or some region proposal generation method, we can get many crops, and on such cropped images we can further fine tune the CNN, and then we can say that, okay, this further fine tune CNN, this is probably much more suitable for my feature extraction task in my RCNN pipeline. So now talking about the classification stage, we have the CNN features. SVM is trained for every object class in the original CNN. Thus, we have like independent classifier per class. RCNN training data preparation for SVM goes like this. An image region that tightly encloses a card is treated as a positive example, while a region correspondingly, let's say, to background is treated as a negative example. So we are taking this example, like thinking of like, okay, we are trying to train a classifier for the car particular class. Okay, it could be some other class also. Ambiguity arises for regions that only partially overlap with the car, right? This ambiguity, this can then be addressed based on the, like intersection over union, IUU based thresholding mechanism. Then we can also go for bounding box regression. So bounding box regression, let us, discuss more details when we'll talk about fast RCNN. So the training pipeline, this is going like this, right? That we are fine-tuning the CNN using the region proposals. This fine-tuning process of CNN is actually happening independently of my SVM classifiers, right? Like they are not connected. These processes are not connected. But yeah, I mean, this is something where we need to start. Then we extract features. Then in my RCNN pipeline, I'm using this fine-tuned CNN to extract features for all proposals. And then on the top of this, we have the SVM classifiers. So let us now, set the background for next lecture. And to do this, we need to think about the limitations of RCNN. And to think of the limitation of the RCNN, think of the pipeline from starting to the end. What's happening? We have a selective search or some kind of such method which generates the region proposals. And we said that, okay, it might be as many as 2000 in number. So you can decide on in your particular implementation of RCNN. And then each of these has to be resized to a fixed size and to be processed using a CNN to extract features. So this itself, you see, like the first is that the region proposal generation mechanism itself, I mean, this is like we are using like something which is not really deep learning based, is an independent process. And the solution of this will come actually slightly later. Rather than that, the other problem which actually we think even before in the first RCNN itself is the fact that you see like let's say this in number of region proposals are generated and then they are shaped and then each of them are processed independently using CNN. So CNN is executed thousands of times depending on like how many number of proposals you are considering. So but this is like really huge, right? Can we not like somehow instead of thousands of times we do it like just once or something like that? So that's a big question. And on the top of this, of course, what we are seeing is a multi-stage training, right? Like we have the CNN, we have the region proposal generation to start with, then we have the CNN, then we have SVMs, all those like training process and everything, they go separately. So this is together an issue which probably we would like to solve. And this is what we see in the subsequent works. First RCNN and the faster RCNN, they try to address these issues. How we will be discussing in next lecture. With this, we'll stop here. Thank you.